How you doing? I'm Mr. Rose, and today we're going to try something a little different. We're going to work through some problems together. As always, I'm going to suggest you go ahead of me uh, prior to solving the problem, but this time we're actually going to write out some problems and then explain things as we go. So, like I said, it's going to be a little different, and these problems are all relating Gauss's law. All right, so to start, we have this charge. And now I've placed this charge, and I'm calling it a positive charge, inside of a sphere. Now the sphere is what we're going to define as our Gaussian surface. And things that we know right now about a charge. We definitely know that the electric field from this charge all points radially outward. And we know that, again, because this is a positive charge. We also know that this is a uniform field. What things go about that? So if I'm going to draw my uniform field, I could say I have an electric field coming this way, coming this way. My field is coming straight. Again, I'm going to try and make it as uniform as possible out from this charge. And now we do know that we have some field, there we go, going towards the camera and away from the camera because, again, this is three-dimensional and a sphere. We know that that field is distance dependent. Right? And we are going to utilize this spherical symmetry because if I know it's distance dependent and I have this, again, this Gaussian surface, this sphere, I can actually label, if I'd like, my Gaussian surface. Maybe I should make it an arrow. Labeling my Gaussian surface, I know I can utilize some kind of symmetry. And the symmetry I'm going to use is spherical symmetry. So what does that mean? That means that my electric field, things that we already know. We know my electric field depends really on a distance. So I'm going to write an electric field is really based on some radius in the r hat direction. Now I actually shouldn't have a vector sign there. So my electric field is with respect to r in the r hat direction. That's any radial direction, which again essentially means, as we've seen in the past, that the electric field depends on the radius. Well, that makes sense. So we're going to apply Gauss's law. Just to recall, Gauss's law is my enclosed integral of E dot dA. And remember, we can think of that dA as some vector, and that is equal to my charge enclosed divided by my permittivity constant, epsilon naught. Now you might be thinking, I don't know what the electric field is. Really, I don't know what the electric field is anywhere, and that exactly is the point. That is what we're trying to figure out, but what I do know and what I can use is I know that the electric field is constant at any respective r, at any respective radius. So if I come some radius, now I know I'm drawing that inside my shell, some three-dimensional radius r, I know the electric field at that three-dimensional radius at that point is constant. I know the electric field on the Gaussian surface that I've already drawn is constant. So what that means is I can use that information. Since I know the electric field is constant with respect to r, I can move this up a little bit. I can say that E dot dA is equal to my electric field with respect to r at any, remember, vector area. So maybe at like either the whole shell, or if I'm going to talk about a small piece, at a small piece of that puzzle, that small patch. And that's what we're going to utilize here. So at this point, I'm now going to apply my Gauss's law. Since I know E with respect to r is a constant, I can pull it out of my antiderivative. So I'm going to have really E with respect to some radius times the surface integral about dA, and I know that equals to my charge enclosed over my permittivity constant. Well, again, we've seen this before. We were talking about this Gaussian surface, this sphere, which means my dA is really just the sphere, 4 pi r squared. So when I'm going to add up that area, all of my dAs, that's just 4 pi r squared. And that equals Q enclosed divided by epsilon naught. Now, if I want to rearrange that just to find my electric field with respect to the radius, we should get something that looks really, really, really familiar. Something like 1 over 4 pi epsilon naught times Q over R squared, where this Q is my Q enclosed. What did we just do? We just showed there is a relationship between Gauss's law and Coulomb's law, which we just proved. So with this information, what did we just do? We're really trying to figure out what Gauss's law does. And Gauss's law is basically a relationship or a special way to look at Coulomb's law, and it takes advantage of some type of symmetry. So Gauss's law relates to some symmetrical object that we are creating. We are creating this hypothetical closed surface to be able to analyze what's going on. And that surface can be anything. In the last example, we just did a sphere, and that sphere clearly showed us, that sphere had some symmetry, which then brought out Coulomb's law to show that relationship. Now, if we're still having a hard time thinking about that, we can think of this clipboard as a screen. You can see me, I can still see the camera, because things are flowing through this. If it was a screen, my example would really be an airflow, but we can think that there's air flowing through this. So if I picture this as a screen and air flowing straight towards you, straight towards that camera, we can say that the velocity of the air going through this screen would be virtually constant. Of which case I can figure out the volumetric airflow based on the area, based on this distance. I can figure out the volumetric airflow flowing through this screen per second, which is something that we talk about flux. And flux is that flow of electric field. I know that's kind of a hard concept, which is why we've talked about air and fluid so much. Flux is that fluid motion, that amount, that volumetric airflow, that volumetric flow of electric field. That's what was coming out of that Gaussian surface. We define that as a capital phi. Our flux is defined as a capital phi, and we know it's a maximum when our velocity is perpendicular to our area. We know it changes. Again, if I go back to my screen, now none of the air is flowing through this because it's going the same, because it is perpendicular, can't see that, perpendicular to my airflow. So this is really how we're putting it all together. In reality, we're going to use Gauss's law, again, this new look at Coulomb's law, really for only two different situations. One type of situation is, say, if we know the charge, we're going to use Gauss's law to find what the field is at some point, some random radius. Or if I know what the electric field is, I can create some Gaussian surface and figure out what the enclosed charge is. I hope this example helped you. If you made it through on your own, well done. Feel free to like, click, or subscribe, and take a look at the next example. Thanks for watching, and I'll see you next time.